Okay, everybody, we're going to move on a little bit and we're going to talk about temperature today. And if we take a look at temperature, temperature is different than heat. So we're going to look at it in a different way. All right. So basically, when we talk about heat, we talked about the fact that the heat is being energy that moves based on a temperature change. But what is temperature? And really, when we think about temperature, and we've taken our temperature a lot, the temperature in the room, the temperature of your body. Again, these days we're taking temperatures to see if we're sick or not. um, is really important, and it measures the how hot or cold something is. Okay, and when we look at this a little further, what we usually do is when we measure things, we usually measure them in either Fahrenheit or Celsius. And again, Fahrenheit or Celsius is simply just temperature scales that we use based on certain points. Okay, so for example, when we look at in this writing here and in the beginning of this thing here, we really look at like temperature in the Celsius scale is really just a comparison of freezing and boiling point of water. So freezing would be 0, boiling point of 100. And Anders Celsius was the scientist who came up with this scale. Daniel Fahrenheit came up with his scale for temperature. But what we want to focus in today is the Kelvin scale. And the Kelvin scale is interesting because the Kelvin scale has an absolute bottom to it. Unlike the Fahrenheit and Celsius scale, the Kelvin scale has a 0 to it that you can't get any lower than 0. 0 becomes the bottom. So let's see what we're talking about when we talk about this. So basically, this Kelvin scale is a different scale we're going to be using. Okay, and when you measure Kelvin temperatures in K, what you're measuring is the average speed or the average kinetic energy, okay, or the motion of atoms and molecules. So that's really what you're measuring when you measure the temperature. Now, the hotter you get, the particles move faster on average, and the colder you get, the slower that they move. All right, so the Kelvin scale directly, measures that average kinetic energy, or is an indication of this. Where Celsius and Fahrenheit simply just, are based on water, and would have, a scale that would be slightly different. All right. So as we cool it, let's just say we had a couple of gases and we were just cooling them down more and more. As we cool them, the theory of kinetics, which is the movement, okay, states that these molecules are going to move slower. Okay, so they're going to move slower as you cool that gas more and more. And as the motion of these particles approach 0, okay, then the volume should also approach 0, right? So the volume, the space that this takes up, should also approach that 0 mark. 0 mark. That's important. So if we take a look at the diagram here real quickly, you see if we had gas A, gas B, and gas C, so we had different gases, and we begin to cool them. So we have a certain pressure and a certain temperature of them. And let's just say we start cooling those gases back. When we cool those gases back, we eventually reach this strange temperature all the way really, really cold, right? So we come all the way back from 100 Celsius here. We cool them all the way back, and we notice that they begin to converge. And as they converge at this point at which the volume of the gas equals 0. Now, if you think about that for a second, the volume of something that's made of mass can't really be 0, right? It can't be. So this becomes a theoretical point where you would have no pressure or no volume. And in that case, you would reach something called absolute 0. And that's the important thing we want to get across here with this. All right, so basically what does that really mean? You can reach the absolute 0, okay, when you hit 0 Kelvin, and that means motion of all those particles would actually cease to exist. You'd have no motion whatsoever. So the Kelvin scale actually has a bottom to it, right? It has a bottom where 0 Kelvin is the bottom line. You would have no molecular motion or no motion at all. You can't go below 0 Kelvin. You can only go up. Where in Celsius, if you have 0 Celsius, you can go negative, right? And in the Fahrenheit scale, you can go negative, but in the Kelvin scale, you can't. So that kind of helps us out here a little bit. All right. So stated simply, okay, the temperature in Kelvin, okay, is directly proportional to, and directly proportional to means as one goes up, the other one goes up in proportion, and we'll see that in a minute. okay, to the average kinetic energy. Okay, and again, that's going to be the motion of the particles. The faster the particles, the higher the temperature. The slower, the lower the temperature. Okay, and that's going to be really important to know. All right, so how do you convert actually from Celsius to Kelvin? And we're going to need to go backwards with this, and just understand something about the Celsius and Kelvin scale is that they're exactly the same scale degree size, which simply means that a Kelvin degree or a Kelvin amount for a Kelvin degree and a Celsius degree are the same size, which means if you go up 1 Celsius, also go up 1 Kelvin, but they're offset by 273 degrees. So really, your Kelvin temperature is whatever your Celsius temperature is plus 273. Okay? And if we go back, if we go back to that in a minute, it's also, um, you can also say your Celsius temperature, okay, is going to be your Kelvin temperature minus 273. So you're going to want to commit these two guys to memorize. Please memorize this. Okay, of course, you will also have this on a reference table, but if you memorize this simple little formula, it'll take you a long way. All right, so to repeat, the temperature in Kelvin is directly proportional to the average kinetic energy meaning motion. Okay, so that's what you study, but that's what you measure when you measure temperature. Really, really important. If we go to the next slide and we take a look at this again, okay, how do you convert? We talked about that before. Okay, and let's just do a little exercise with this on how we actually convert from this. Okay, if we take our Kelvin temperature, what we would do with Celsius? Well, we would have our Kelvin temperature, right, minus 273, and I would get 0 Celsius. Well, go 0 degrees Celsius. Okay, so 273 is 0 degrees Celsius. Again, we can also take my Celsius is Kelvin minus 273 here too. We can say that also. Okay. Now let's just say we had 50 Celsius. I would plug 50 Celsius in here, and if I wanted my Kelvin temperature, I would say 50 Celsius plus 273 here. All right, and I would get 323 Kelvin. So I know the numbers look a little weird. They're a little high from what we're used to, but it kind of works. Here, you would have 150 Kelvin minus 273, right? And that would give us negative 123 Celsius. All right, so just understand that the Celsius scale and the Fahrenheit scale can have minus signs, but the Kelvin scale cannot, right? All right, and again, the same kind of thing here. If we take 150 Celsius plus 273, I would have 423 Kelvin. All right, so we want to know that. Important stuff. Okay. Interesting here, we can ask the question, does a gas, and this is like your region-based questions here, does a gas at 100 Celsius have twice the kinetic energy as a gas at 50? And you might say, well, yeah, it does, because 100 is twice 50. But you got to be careful. When you explain this, you must look, okay, at the Kelvin, okay, in order to make this. Just because you have twice Celsius doesn't mean you have twice the Kelvin. So if we take 100 degrees Celsius and we add 273 to that, we would have 323. Sorry, 373. All right. And if we take 50 Celsius and we add 273 like to that, that would be 323. So my question to you is 373 twice 323? And the answer is no. So no is the answer to the question. Okay, you must change to Kelvin. Okay, 373 is not 2 times 323. Okay, so that's important to know. So you must change to Kelvin. That's the big idea here. Okay, and again, we can look at the bottom here too. With these, I think these little things here. It says, which of the following samples of alcohol has particles with the highest average kinetic energy? And you want to think the highest Kelvin temp, not degrees Celsius, or mass. We don't care what the mass or the volume is, right? So just because we have 400 here doesn't mean that's going to have the highest kinetic energy. Remember, you're moving faster when you have the highest kinetic energy. All right. So if you take a look at this, okay, this is already in Kelvin. We'll leave it that way. This is already in Kelvin. We'll leave it that way. But 30 is going to be 303 Kelvin. Okay, you want to convince yourself of that. Take 30 times 273. Okay, 35 Celsius is going to be 308 Kelvin. Okay, so let's examine all the Kelvin temperatures now. We have 303, 273, 308. That makes letter D the right answer. Okay, because that's what we want to see when we have the highest average kinetic energy. So thinking the temperature in Kelvin, that's the important thing to know when we look at this. So I just want to go back to one thing. To go back a notch and just show you a quick uh, little view of this. And what you're going to see on this is a little viewable thing on this. If we go to states of matter on this, and we take a look for a minute at gas. Okay, if we look at the gas phase, because this is easy to see. And even if you look at the liquid, or even take a look, the gas phase is easy to see. You'll see that on this, there's a lot of particles moving around randomly. And what we talk about the average kinetic energy is we talk about the average movement or the kinetic energy of all the particles. And you can see there's a couple of particles here that are moving very slowly, and there's a couple of particles that are moving very quickly, and there's some somewhere in the middle. So when you look at the average kinetic energy, you're really looking at the average motion of all these particles and the energy they impart on each other in the walls of the container. Now, if I was to heat this, okay, I would also add some heat to this. I would transfer heat into the kinetic energy of the particles, causing the temperature to rise. So if you look up here at the temperature rise here, you can see it moves quickly. All right, of course, if we were minus 92, and we move that down, but you get the idea, so we can put that back where we were, 81 Kelvin. If I begin to heat, and I bring this up higher, I might see this average kinetic energy of the particles. You can see some of them are actually moving a little quicker and quicker and quicker and quicker now. They take on more of that speed. Now, again, more likely you're going to have particles moving at faster speeds and slower speeds when you have this highest average kinetic energy. All right, so that's interesting to know. Even if you see a liquid, you'll see some of them are moving quicker than others. Some of them even are escaping. And in a solid, there actually is motion also. So your average kinetic energy in a solid, of course, would be lower for a liquid or a gas, given what you have. Of course, I think in the phase changes, you could probably see the same thing. Again, if I begin to heat this, you'll see your average kinetic energy increase until you melt. All right, and you can actually see that that's the way that goes in that way. I think in oxygen, if you had that in that, and maybe if you can move it a little bit, but you get the idea. I mean, you can see that obviously it's an average motion. Okay, so I wanted to just show you that. And that's it. So really what you want to know is average kinetic energy is a measure of the temperature, or temperature measures average kinetic energy in Kelvin. You want to be able to calculate Kelvin and Celsius back and forth, okay? And that is what temperature is. It's different than heat. Heat is energy that moves due to a temperature change, okay? And temperature is the average kinetic energy, okay? And we'll talk to you soon.